So for this lesson, we are going to be talking about current division and doing an example with current division. Now, current division deals with parallel circuits. And the reason it deals with parallel circuits, we know that circuits in parallel have the voltage all being the same, but the current, we said, is typically not the same. And so we're wondering, well, how does that current divide down amongst the different components? So let's again just kind of look at a figure here. I'm sorry, that shouldn't be a voltage, this should be current, because we're looking at current division. Now let's say we want to find I1. Well, we have a current source here, I'll call this I, that's coming up, and then it's dividing amongst these three resistive branches. And we want to know what the current I1 is. Well, remember, again, we said this is in parallel, so the voltage we know is the same across any of these components. The voltage that I measure, and I'll even put one more here, these are all the voltage V. So I do know that V is going to be I1 times R1. I mean, we also know, I'll put it off to the side here, that V would be equal to I2 R2, and that V would also be equal to I3 R3. And we have one more here, that V has to be equal to I times R equivalent. So it's the current that's coming up through this current supply times the equivalent resistance here. So of course we're wanting to find I1. Well, actually right here, this is going to be pretty quick. We know what the current I is. That's what we're given. And I can see that I could substitute then for V, or set these equations equal to each other. Since the voltages are the same, I know that I times R equivalent is going to equal I1 times R1. Which of course means that I1 is just simply equal to R equivalent over R1 times my current. Now this is the formula I like to remember, and I like it because it's really just kind of the reciprocal of the voltage division formula. Remember the voltage division formula, I'll scroll back here. Voltage division formula was Rn over Req times voltage. Well, now for current, we're getting Req over R1. So if we wanted to write for a general current, In would be Req over Rn times the current supply. Now, there are different ways of writing this. If we use admittance, we know that admittance is Y is equal to 1 over R. So I could write then that this would be In is equal to 1 over Yeq divided by 1 over Y1 times I, which this simplifies to In is equal to Y1 over Yeq times I. Now this honestly is the reason I think some people like to use admittance, is then if we look at this formula is in the same format as the voltage division, except instead of using resistances, you're using admittances. So IN is not Y1, it would be YN, or yeah, YN here. This should be a YN. It's in the same form as the voltage division. However, I will emphasize this is what I will use. Now that does not mean you have to use this one. I'm a big advocate that if what you're doing is correct as far as formulas are correct and your math is correct, and it's not the way I'm doing it, but it's still a valid approach, I'm not going to mark you wrong, because it's not about doing it my way. It's about understanding how to analyze circuits. And if you do it a correct way that's different than, quote, the way I would do it, well, then I should still give you full credit, because the point isn't about doing it my way. It's about understanding how to analyze circuits. All right, so let's look at an example here of this. No, I don't want that to go away. Okay, so I want to know here, I'll just label them here, I1, I2, and I3. I want to know what all three of these currents are. So find I1, I2, and I3. So just remember here, I1, for instance, would be Req over R1 times my current. I2 would be Req over R2 times my current. And I3 would, of course, be Req over R3 times my current. So really, there's not a lot to do in this problem. I just have to find Req. And Req would simply be 1 over 10 plus 1 over 6 plus 1 over 18 all to the negative 1 power. And let me do that on my calculator real quickly. Yeah, we get something that's not necessarily a pretty number. I get that this is 3.103 ohms, which if you, I mean, that's the way I would write it, but if you wanted to, some calculators like to store them, or you can have them stored as a fraction. And if you did it as a fraction, this would be 90 over 29. But I really don't think that's necessary to do. As long as we have this to a few decimal spots, that will be good enough for us. Now, when you get into measurements and significant digits and things like that can be important. But again, even if you're talking about significant digits, you really wouldn't need 90 over 29. You just need an extra digit compared to what your significant digits are. So we're just going to leave it at 3.103 ohms. So then to get I1, it's just 3.103 ohms divided by 10 times 10 amps, which would be 3.103 amps. I2 is going to be 6 ohms divided by 10 ohms. I'm sorry, 3.103 ohms divided by 6 ohms times 10 amps. And if I do that, we get 5.172 amps. And then for I3, it'd be divided by 18 ohms times 10 amps. And you'd get 1.724 amps. And so these would be the three currents. Now let's go ahead and do the same thing we did with the voltages. Let's sum them up. And so let's do 3.103 plus 5.172 plus 1.724. And if we add all of those up here, we wind up with 9.999 amps, which of course is just 10 amps. Now, technically it should add up to exactly 10 amps, but we're adding up to 9.999. Hopefully we can all see why this would be the case, that we're not getting exactly 10 amps. And the reason is, of course, because we approximated what the equivalent resistance is, because we used the approximation of 3.103 as opposed to the exact number of 90 over 29. But even when you use approximate ones, you can see that when you sum the currents up, you're getting that the current going through those resistors is equal to the current being delivered. Now the other thing we should point out here is that the smaller the resistance, the more current we get. Which really shouldn't surprise us at all. I mean, talking about voltage and current here and resistance, and we've said that, hey, you can think of resistance as like resisting current flow. So we shouldn't be surprised that we get more current the smaller the resistance is. So, you know, that's what we get, which, again, shouldn't really surprise us. All right, let's end this video here. The next thing we'll be talking about is something called nodal and mesh analysis. A lot of textbooks like to make this a lot more complicated than it really is. We're going to go through that really quickly and then do a couple examples, and then we'll start getting into some applications. So nodal and mesh analysis is kind of the last, analysis technique we need for this course before we can start getting into some applications.